Hello all. Today we discuss about VHDL programming of 8:3 octal to binary encoder. So first of all, what is encoder? Encoder is a basically digital circuit which convert input information to corresponding here 0 to 1, 2, 3, 4 up to 7 and 3 output active high output named as y1, y2 and y0. So the signal name as y2 is to 0 because this is 0 to 12th bit and the information bit are 7 to 0. Okay, and this is 8:3 octal to binary encoder. This is basically the encoder circuit. So now this is the logic written in a VHDL. There are two IEEE standardization library. One is IEEE standardization library of standard logic and another for IEEE for HDL. Now this is for entity of encoder. Here one input is known as I symbol, and these input are 8 inputs are available. Therefore the signal bus are 7 down to 0 and the output are y. This is the 3 bit, this is 2 down to 0, and here the behavioral model are structured. First of all, process our information bit. If information bit equals to 1 and remaining all other 0, then output equal to 1 1 1. That means this is equal to the equivalent output of 7. Okay, now again next when 0 1 0 0 0, so this is the equivalent output of 6. This is for 5 and so on. And one thing should be remembered: if no one input is selected, then output is high impedance state. This is known as high impedance, or also known as don't care state. Okay, that is no binary output are coming or no input are selected. This is here the end process, and this is the behavioral ending. Now if we simulate by using check syntax, first of all this is check syntax. Okay, save it. After some time this is shown by green color and right symbol. That means our code is, there is no error in our code, and there is shown that process syntax check syntax complete successfully. If we view the technological hardware schematic diagram for 8:3 encoder or octal to binary encoder, so after some time running the synthesis, and this is our whole logic diagram, internal logic diagram of 8:3 or octal to binary encoder. This is an RTL schematic. Now this is an input information bits, and each block maintain the hardware. Now if we click the hardware here, if we click this logic block, then we show the equivalent logic diagram, the equation and the truth table and the Carnot map also. Okay, next one, in the simulation, if we select the simulation and simulate behavior model, now we analyze our test bench analysis. So first of all, these are 8 signals and these are 3 output signals. Okay, now click here and here click force constant. Here the 8 inputs, that means first of 1 and remaining all other 0 0 0 0. Now they apply and OK and run here. This is called the run of the time specified on the toolbar. Now see that when this is 1, that means this I7, now this is the signal pin condition. Look here that this I7 pin equal to 1 and remaining all other bit equal to 0, therefore output gets 1 1 1. Okay, it's very, that means if we select 0 1 0 0 1 2 3 4, now we select the 6th number of input, therefore output becomes 0 1 1 0. So here show that 1 1 0 and here show that this is 0 1 0 0. So again one example, if we select 0 0 0 0 0 0 1 0, that means 2 is select. Now the output equal to 0 1 0. Okay, no, sorry, this is 0 0 1. I'm sorry, because this is 1 select. Okay, the input information bit is 1 is select, and this is the output. Okay? shown in the test bench from. Okay, so this is the analytical process by which we can simulate or you can test our test bench analysis in a hardware description language, and this code is downloaded in the PGA kit to run the specified encoder circuit operation.